All right, here we go. So today we're going to learn about rotational inertia. All right, honestly, most of this is stuff that we learned in honors last year. So there will be a little bit of review, but there's also a little bit more about sort of where all this comes from and a new theorem called the parallel axis theorem. So take a second, read through the learning targets here so that you know kind of what to watch for. This video is actually split up into two chunks. 12.1a is going to be algebra stuff. All right, and then there's a 12.1b, which is going to ask you to memorize some kind of derivations, or better yet, I should say understand some derivations. But I say memorize because there's just a few of them, and once you learn those few, that's kind of all you need to know. So anyway, here we go. So what have we learned? Well, so when we talked about Newton's laws, we learned that the net force acting on an object is equal to the mass times the acceleration. Or maybe more usefully, the acceleration of an object depends on the net force, the total of all of the forces pushing or pulling your object, divided by the mass. Okay. Now remember, when we talk about mass in physics, we define mass as a measure of an object's inertia. It's resistance to a change in motion. Okay. So the idea is, as an object has more mass, it has more resistance to a change in motion, and that will necessarily decrease your acceleration, assuming that your net force is fixed, right? So in English, when you push a thing with a fixed force, the more mass it has, the more inertia it has, therefore the less acceleration it will have, okay? So recently we've been talking about angular acceleration, okay? And we've learned that that is produced by a net torque, right? Well, it turns out that there is an angular counterpart to mass, and that angular counterpart to mass is what's called rotational inertia, okay? And so we need to learn this video a little bit about this idea of rotational inertia, okay? So an object that has a larger rotational inertia just means that it is harder to change the angular motion of that object. Okay. So we will dig into using this equation a little bit more, I think, in the next video, like 12.2. But before we do, we really need to learn about what this rotational inertia is. Okay. So it turns out that for a let's see what we got. So rotational inertia. So I, capital letter I, is the symbol for rotational inertia. In older books, they tend to call it moment of inertia. So if you hear the word moment of inertia, that's the exact same thing as rotational inertia. You don't hear that term as often anymore. But as I said a moment ago, rotational inertia is just the rotational counterpart to inertia or mass. Okay, and it's a measure to an object's resistance to a change in angular motion. And it turns out for a point particle, I is equal to mr squared. So if you've got some point with mass m, oops, and then it's maybe it's rotating about this axis. So there's a vertical line, so our object is going to be kind of coming out of the board like that. So to calculate the rotational inertia of this particle, you need to know the mass, and then the radius of the circle that you want it to orbit. And so the rotational inertia is then mr squared. And notice, the bigger the radius is, the more inertia it has. All right? So where does this equation come from? Well, when we get to rotational kinetic energy, I'll give you maybe a clearer explanation of why it's mr squared. In the past, I've done that first, but it never seems to make as much intuitive sense. So we'll do rotational kinetic energy later. For now, just kind of take my word on it that this is the equation for rotational inertia of a particle. And like I say, we'll learn more about it later on. But the big thing that I want to make sure you get out of it at this point is this last idea, that the farther the mass is from the axis of rotation, the more inertia it has, and therefore the harder it is to change its angular motion. Okay? So, there we go. All right? Now, what if we've got something that's not a particle? Like, what if we're talking about, like, the rotational inertia of a wheel, or a hoop, or a ball, or, like, a stick that we're rotating? Well, then what you do is you take a summation. You take every single particle that has mass, you multiply the mass of each individual particle by the radius for each individual particle, and then you add them up for all of the particles, okay? But with a real object, like if you're trying to find the rotational inertia of a door, you don't want to literally add up all the particles, each individual molecule, or each individual electron and proton and stuff, right? That would take forever, right? So eventually it becomes calculus, right? So it's r squared times the mass of that. So it's r squared times the mass accumulated at that radius, okay? And then you integrate it. So an integral is kind of like an infinite summation, Okay. So video 12.1b will show you how to use this equation a little bit more, okay? And I'm not going to worry about that right now. But so this is how you calculate the rotational inertia for a thing, and I'll talk more about that in video 12.1b. But it's important because this equation tells us where all of these equations come from, all right? And you've seen these, right? These were on the back of your honors tool, your honors equation sheet last year, right? And so the big thing I want to make sure you notice, and I did not stress this earlier in the video as I meant to, is that the rotational inertia doesn't just depend on the shape of the object, it also depends on the axis of rotation, okay? Because here we've got two thin rods, right? Here's a thin rod, and here's a thin rod, okay? But they're rotating about different axes, right? So here, your axis of rotation is running through the center, okay? And here, your axis of rotation is running through the end, okay? And in both cases, I is 1/3 mr squared, but r means something different, right? For the top one, r is the distance from the axis of rotation to the end of the board, but notice that's just half of the total length, right? So that's what r is here. Whereas here, r is, again, the distance from the axis to the end of the board, but this time that r is now the length of the whole board. Okay, so you have to be careful and make sure that you look at the drawing so that you correctly interpret sort of what r is. Okay, so those are two different types of rotational inertias for a rod about the center and a rod about the end. A plane about the end is the exact same thing because notice the width here doesn't matter, so this width doesn't matter, which means this is still 1/3 mr squared, and this is still 1/3 mr squared, okay? All right, and then there's some other ones. So, like, you've got some circular objects. So, in the upper right-hand corner, you've got a disc, that's basically a solid wheel. You've got a hoop. So when we talk about a hoop, we're talking about an object where the thickness of it is very small compared to the radius, okay? And then we've got two spheres. One of them is a solid sphere, and the other one is a spherical shell. In English, it's hollow, okay? So this would be kind of like a bowling ball, and this would be like a basketball, okay? I guess a bowling ball without any holes in it, but all right. Okay, and then this last page just has a few weird ones. Here's one where it's still like a hoop, but now you've got two different radii. So like, maybe it's a little bit fatter, so like a donut, right? So you've got an inner radius and an outer radius, where there's a significant difference between the two. This is just a disc again. Notice again the width this way doesn't matter, so a cylinder or a disc is the same. I think the only other ones we might use are, I feel like there's at least one homework problem that has this, and I know for a fact there's one of these. Actually, I say I know for a fact. I may have deleted it, but so anyway. So those are some different shapes and different axes of rotation. Cool. So let's do a real quick example then of one. All right. So let's calculate the rotational inertia of a meter stick. So I of a meter stick. Now notice when just saying that is not enough. You can't calculate the rotational of a meter stick. Okay. This is supposed to say I of a meter stick. Okay. So you can't just calculate the rotational inertia of a meter stick unless you define the axis of rotation. Okay, so let's find the rotational inertia of a meter stick about its center of mass. And the mass of a meter stick is usually about 60 grams, so we'll call that 0.06 kilograms. So I is 1/3 mr squared, because that is, if you have lost track, a meter stick is going to be this guy, right? And it's about the center of mass, which runs through the middle, so 1/3 mr squared. Okay, so here we go. So that's 1/3 of the mass times the radius. Well, your meter stick looks like this. Oops. Here's your axis of rotation. So r is half the length of a meter stick, half of meter, so 0.5 meters, right? So 0.5 meters. Don't forget to square it. And so that gives you 0.25 times 0.02 is 0.005 kilogram meters squared. Because this is kilograms and this is meters. I'm nervous about that number because I've done this wrong twice. 0.02 times 0.25, 0.005. Cool. Okay. Now, what if we wanted to do it about one end? Well, then my mass is farther out, so I should have more rotational inertia, right? So now my R is 1 meter. Okay. All right, if I want to find the rotational inertia about one end. So then it's 1/3 times the mass times the radius squared, and that gives you 0.02 kilogram meters squared. Notice a larger rotational inertia because now you've got more mass farther away, right? And R squared here, you've got more mass that's farther out. Okay? All right. So finally, all right, so suppose we wanted to do something like this. So we've learned how to find the rotational inertia of the meter stick about the center of mass and about one end. But what if we want to find the rotational inertia about some random point in the middle? Okay, like this. Maybe we want to find the rotational inertia of a meter stick about the 20 centimeter mark. All right, so to do that, we have to use what is called the parallel axis theorem. All right, so it turns out if our axis of rotation is not at the center, then we can use what is called the parallel axis theorem. So what this says is that the rotational inertia about some pivot point, about some arbitrary axis, is equal to the rotational inertia about the center of mass plus mh squared, where h is the distance between point P and your center of mass. Okay? So in this previous example here, we're trying to find the rotational inertia of the meter stick about the 20 centimeter mark. So what we would do is we'd go, okay, well, the rotational inertia about the 20 centimeter mark is equal to the rotational inertia about the center of mass plus mh squared. Okay, so let's see. I about the center of mass, well, that's 1/3 times the mass times R squared. Now remember, about the center of mass, your R would just be half a meter, right? So this we'd figured out before. Okay, so that's the, whatever it was, 0.005, okay? So notice our center of mass would be here at the 50 centimeter mark, right? And this is the 20 centimeter mark. So here, oops, so here our h would be the distance from our center of mass to the point, our new point, P, which is 30 centimeters or 0.3 meters. So this is going to be plus the mass of the stick times 0.3 meters squared. Okay? So this is our h, oops, 0.06, sorry, got my decimal in the wrong spot there. Okay, so this gives us the 0.005 plus, let's see, what is 0.06 times 0.3 squared is 0.0054. So add them up and you get 0.0104 kilogram meters squared. All right, so that's how you use the parallel axis theorem. Okay. So let's try one that's maybe a little bit more involved, all right? So this one is a good one because it shows us two things. This next example shows us two things. One, it's going to show us another use of the parallel axis theorem. Two, it shows us that in the same way that you can add masses of two objects, you can add rotational inertia of two objects, okay? So here's our last example, all right? So now we've got 2 meter sticks. All right, this time we're just going to use the generic term m for mass. And they're attached as shown, all right? And they are going to be pivoting about this axis here, okay? So the first thing I'm going to do is, so the rotational inertia here, let's call it total, is equal to the rotational inertia of the vertical stick plus the rotational inertia of the horizontal stick, okay? So the rotational inertia of the vertical stick is just the rotational inertia of a meter stick about one end, right? So I about a stick around one end is 1/3 m times r squared. Well, here r would just be 1 meter, right? So that's just m over 3. So that's the rotational inertia of the vertical stick. All right, now the rotational inertia of the horizontal stick, well, that's equal to, let's see. So this is the center of mass, but our pivot point is actually 1 meter away from that, right? So I'm going to use the parallel axis theorem. So I'm going to do 1/3 times the mass times 0.5 meters squared. So that's the rotational inertia of this stick about the center of mass. But now I got to do plus mh squared. So plus m times h. Well, how far is my center of mass for that bottom stick from my pivot point? Oh, well, that's 1 meter, right? So times 1 squared, right? So this gives me, well, this is a fourth times a third, so this is m over 12 plus m, that's 13m over 12. So that's the rotational inertia of the horizontal stick. So then the whole rotational inertia of the whole thing of these two sticks is m over 3 plus 13m over 12. So this is the same as 4m over 12 plus 13m over 12, right? Using common denominators, it gives you 17m over 12. So there's the rotational inertia of our 2 meter sticks. And now if we knew what m was, you could obviously plug that in. Okay, so 2 morals here. 1, you can simply add rotational inertias to parallel axis theorem. Parallel axis theorem comes up very, very frequently. And when we get to objects rolling, we're going to be using it a lot. All right, there you go. How did I do on time? Cool.